Hi, everyone. Welcome back to another exciting edition of data analysis in physics. Today, what I'd like to do is talk about the role of the prior in Bayesian analysis, and talk about some techniques that move beyond what we've done here earlier into a slightly more sophisticated approach to these prior distributions. Now, as I said, the key difference between a Bayesian analysis and a frequentist analysis is that a Bayesian analysis always declares and incorporates prior information into the framework that we're studying our data. And so far, we've kind of focused on uninformative priors, which simply said, for example, the value is somewhere between some minimum and some maximum value. But in the case that we want to study today, we'd like to go over a slightly different uninformative prior and get into the study of conjugate prior distributions, which are a really useful and powerful tool for certain classes of problem. The uninformative prior I want to bring up is called the Jeffreys prior, after the statistician of the same name. And in the Jeffreys prior, what you're looking for is an uninformative prior for data with an unknown scale. Now, to contrast that and sort of set this up, what we've been doing so far in using our uninformative prior is just to assume a uniform data distribution on a variable x arranged between x min and x max. So it's somewhere in this range, and we didn't really know where it was. And so we parameterize that by sort of saying we don't know where the location of this point is. And so we'd expect for a prior that the interval of the prior conditioned on background information as a function of dx is going to be roughly translation invariant. So if I add a constant c to that value, I end up with about the same value. And so if I expand this differential, you find that so d of x plus c is about the same as d of x, just using the rules of calculus. And so that means that the p of x conditioned on I is approximately equal to p of x plus c conditioned on I. It's basically a statement of a uniform prior, but it is saying it in a way that just sort of says we don't know the location of the data. Sometimes we're less sure of the scale of the problem. Say, for example, coming back to measuring the mass of Saturn. In this case, if we had no awareness of what a planet's mass is, it could be anywhere from, say, an Earth or a moon mass even, up to, say, the mass of the sun. And that's a huge range. And if we assume a uniform prior, what happens is that most of the sort of weight in that probability function is going to be at the top end, sort of near the scale of the mass of the sun. But we don't actually know where it is on this scale parameter, so we write down in a similar sense, we say that the p of x given background is going to be approximately equal to p at beta of x. So where beta is some real number that's scaling my factor, and then we expand the differential here to get p of beta x times beta dx is going to be equal to p of x. And this really only works if we have a probability density function that scales like 1 over that parameter, so that every logarithmic interval is uniformly weighted in our prior distribution. And so that's essentially the Jeffreys prior says that there's a uniform distribution in log space between some parameter x min and x max, say the mass of the moon to the mass of the sun. And that allows the parameter to kind of float and probe those values closer to the bottom end naturally by incorporating the sort of unknown scale of the mass of the problem. So if you have something that is naturally treated in a logarithmic space and you really don't know the scale of the value, say, did your data come in microns or nanometers, and you don't know for sure, this Jeffreys prior is a very good way of kind of treating the prior distribution there. It's still uninformative, but it's basically logarithmically uninformative rather than linearly uninformative. But that's one of the it's another sort of simple approach here. A slightly more sophisticated approach is the technique of using what's called a conjugate prior distribution. And the idea here is that in Bayes' theorem, you are multiplying a prior times a likelihood. And if you choose a prior that has the same sort of functional form or a friendly functional form as the likelihood function, then the product of the likelihood times the prior, that right-hand side of the Bayes' theorem, becomes a nice tractable function that we can understand and use, and it gives us mathematical insight into the role of the prior that we're selecting. And as a sidebar, I'll sometimes refer to the parameters in this prior distribution as the hyperparameters. So the hyperparameter of the problem is what's describing the probability density function of the prior distribution. So as an example, let's go all the way back to the coin toss here. And we had this case where the coin toss had a probability of landing with a value h. And for this, a really natural prior is to use this beta distribution, which I kind of referred to earlier. And a beta distribution has this form shown here, that it's the product of some gamma functions times h to the alpha minus 1, 1 minus h to the beta minus 1, where alpha and beta are the hyperparameters. And you'll notice that that h times 1 minus h kind of product shows up here in the likelihood function as well. So we have the likelihood here, and then the prior distribution here. And so the n choose k parameter and the gamma functions, all of those kind of act as kind of constants for a given value of sort of realization of the data. And so you can sort of look at this as proportional to h to the k plus alpha minus 1 and 1 minus h to the n minus k plus beta minus 1. So this gives us these two kind of functions here, and the similar form of the likelihood means that they kind of merge together and then form another beta distribution. So the if we assumed the previous prior distribution, which was a uniform prior, we ended up with a maximum, a mode of the posterior distribution that was just k over n, so the mean number of heads per total number of samples. But if we instead go and we look up where the mode of a beta distribution is, it shows up at a value of k plus alpha minus 1 and plus alpha plus beta minus 2. And this is equivalent to essentially saying we are adding a count of alpha minus 1 heads to the count and beta minus 1 tails to our count. And we often call these the pseudo counts. So essentially we're saying where a prior distribution is essentially modeling the case where we have done the experiment already and we've come up with alpha minus 1 heads and beta minus 1 tails, and then we're going to start with the real data. And you'll notice that as the k and n get very large compared to the alpha and beta counts, this converges to the uniform prior result. All these extra terms drop out and k over n becomes the limiting case. And so that shows a good behavior, and it offers this kind of interpretation for how the prior results are converging. But it's also nice because we don't actually have to do much with the numerical optimization or anything like that. We know it's a beta distribution, and we can go on to any number of reliable pedia websites and like Wikipedia and look up what the properties of a beta distribution are. So bringing back to the illustration of the rule of prior that I showed in the first lecture here, we showed that we had this biased coin, and we put down three different priors. There was the ignorant prior, which is sort of uniform on 0 to 1. Then I had this beta prior of 20/20 there, and then the arcsine prior. But now With the interpretation that we have from this earlier work, we can actually see that this is a very aggressive choice of priors. So I was complaining to you that at 30 counts, we were getting good convergence for the ignorant and the arcsign priors, but this beta distribution here was not coming off of its initial estimate at 0.5. And now we can actually interpret this. It's essentially saying, well, what I have put into this problem is 20 minus 1 or 19 additional heads tosses and 19 additional tails tosses. So that would naturally predict a distribution that's around that center at 0.5. Whereas our conjugate, and so our conjugate prior framing allows us to interpret how aggressive that prior was. And here, if we had good reason to say, well, I really think it's around 1, and I'm going to really, or around a half, and I'm going to really require it to have a lot of evidence past that, of course, it's going to take hundreds or, several hundred experiments to pull it off and make these initial 38 coin tosses that I've imbued into my prior information into something that's that is more dependent on the data. Similarly to the coin toss, we can use something that's a little more useful in physics, and that's a Poisson distributed variable. So if we want to find the PDF for a number of counts given some rate capital R, it goes like the distribution shown here. And if you look at this and you study some statistical distributions, that is very similar to a gamma distribution. And a gamma distribution has this functional form, gamma of x, with two hyperparameters, alpha and beta. It goes like some normalization factor, x to the alpha minus 1, e to the minus x over beta. And so you'll notice here that x is kind of taking the role of r. And so this is r to some power e to the minus r would make a good functional form reminiscent of the Poisson distribution. And I'll note just briefly, notationally, I'm going to write out the names of distribution as letters and then reserve the gamma, Greek letter gamma, to represent the gamma function. So this turns out to be a good prior here, and you can write down the likelihood, which is the product of all these. I've absorbed some normalization constants in here. And if you sort of multiply this out and do some algebraic operations, you'll discover that if I choose hyperparameters alpha and beta, and I multiply it by a Poisson distribution, I end up with a posterior distribution, including this conjugate prior, of alpha, it's a gamma function distributed with parameter alpha plus the sum of the count values divided, and then the equivalent of the beta is the harmonic mean of beta, and then beta minus 1 and n. So this gives you this nice kind of relationship between these kind of two parameter distributions. So if you're not familiar with what a gamma distribution looks like, here's some different illustrations of alpha and beta. It starts out just as an exponential, so that would correspond to that x term being raised to the 0 power. So it drops off like an exponential, and then if I have the power increase, that causes the function to kind of rise up and then sort of fall off. So the beta, the larger the beta, the more it's sort of stretched out along the horizontal axis. And then the different powers of the alpha determine the rise of that function. So that gives us our kind of general shape of what this Poisson distribution looks like. And indeed, this kind of looks like a Poisson distribution. All right, so once again, we have a nice posterior function with a sort of simple functional form, which is this gamma distribution when we multiply things out and do the simplification. And that gives us these two parameters of the posterior, which we interpret alpha as kind of a pseudo count of observations. So it's the number, the ni are the number in a given bin at some number of observations. And then alpha is kind of the sum of the number of additional data that have been collected. And then n is the number of bins over which the observations are distributed. And then 1 over beta is thus the different number of bins over which the prior data are found. So if you assume that you have 20 counts over a very broad bin, you end up with a very 1 over beta is a very large factor, so it's quite stretched out as a result there. So the result of this posterior looks a little like this. So I've gone ahead and I've shown the posterior distribution for some Gaussian, some Poissonian random variables that I generated, but the n is 0 here. So this is just the graph of the prior. I've assumed a gamma distribution with a alpha parameter of 5. This should say r here. And then the beta parameter here will be 1. So it's a nice broad distribution, as sort of shown, and it gives us this nice wide prior here. And then as I incorporate more data into this, so if I add a single datum into it at some bin count, I don't know where it is, it starts to form up. And then as I add progressively more and more data into this, the posterior distribution sharpens up further and further. And every one of these plots that I'm showing is a gamma distribution, but is the posterior is converging to a specific shape and location here. So again, the nice feature of having this conjugate prior is that we get a closed, a known posterior distribution that's a function of the hyperparameters and the data. So for that, we can take a known gamma distribution with these parameters, alpha and beta, and then the mode of that is alpha minus 1 times beta. And so we can use the gamma distribution here for the posterior of our problem, where the alpha and beta parameters become these additional parameters here. And then we just take the product of alpha minus 1, the first argument, times minus 1 times the second argument. And that gives us our estimate of the maximum likelihood given some data and our parameters here. So this functional form immediately gives us our peak, and as the sum of the number of binned data gets large and the number of bins get large, then this converges to the original estimate with a uniform prior distribution. Similarly to the Poisson distribution, we could also treat the problem of finding the mean of a set of data drawn from a Gaussian variable with unknown mean and known variance. It's generated from a set of data xi. Here, if we assume that the prior is a normal distribution with mean mu naught and variance sigma naught squared, the resulting posterior is just a Gaussian, because a Gaussian times a Gaussian, you can rearrange the exponential terms, and you'll find that the mean of the product, after a great deal of completing the squares, is essentially a weighted mean of a variance weighted mean of the prior mean with the new mean of the data. And so that value carries up. And then the variance in the estimate, so as the posterior estimate, shrinks with that 1 over n. So the variance is going down like n in the large limit of large n, so it goes to the square root of n. As an example, I just drew some data from a Gaussian. This is the log of the number of data, and I'm kind of iteratively updating the mean as we go. I assumed a posterior distribution, and you can see that has a different mean from the true mean. And you'll see that the sample mean, which is just what you would get when you do x, sum of x over n, and the posterior mean, those converge together as the number of data get large, though you start out with the result pulled toward the posterior mean. So the final case we can consider is what happens if we have a Gaussian function with an unknown variance. And in this case, we assume a conjugate prior distribution from an inverse gamma distribution. And so we note that as an inv gamma, alpha, beta as the hyperparameters. And that leads to a functional form here where it's a function of the variance here shown as sigma squared raised to the minus alpha minus 1 power for the variance. And that's what makes it an inverse gamma function, is that the variable is appearing in the denominator rather than the numerator where it shows up in the gamma distribution. So it shows up here, and then e to the minus beta again over the sigma squared. So this looks a lot like where you would want your sigmas in a Gaussian distribution. And so the posterior then is a inverse gamma function as well over the variance of alpha plus n over 2, and then beta plus a half, and then the sum of the data with respect to the known mean quantity squared. And if you have this nice posterior function, that has a mode here that is beta plus the sum of the squares of the data over alpha plus n over 2 minus 1. And here we interpret our results of having there are 2 alpha pseudo counts of data added to the sample by virtue of the prior with variance beta over alpha. And so this gives us a nice way of interpreting the case where we don't have a variance, but we do know the mean of the data. Now it's probably worth noting that we've done unknown mean and unknown variance, but often we have a sample of data where we don't have either the mean or the variance. And so in that case, what we want to do is to actually multiply our 2 priors together, use an inverse gamma, and use a normal for the mean, inverse gamma for the variance. And when you do that, you get a combined functional form, just called the normal inverse gamma, that has the additional parameters of alpha, beta, the variance around the mean, and the unknown mean. And that also has a clear posterior distribution with appropriate properties. So it just shows that all of these things kind of look like the same argument eventually as you're going on. And the unique part about a lot of these things is that they are all, a lot of these distributions, they all belong to a family of functions that are called the exponential family. And most of our PDFs live in an exponential family, and if they fill in with this general form where you have functions of the data, functions of the parameters, data xi, parameters theta, and then is exponential of some complex functional sum of the parameters and the data, you almost always can find a good conjugate prior that's in the same family and then determine the properties of it out of that. So this illustrates a bit of the framework we use for setting priors and why some are particularly useful. They incorporate informative priors. It may seem like cheating, but if you are actually good about choosing your parameters and hyperparameters and interpreting their impact on your results, you end up getting very stable initial estimates with a few data. So you can actually get a lot more information out of a few data if you rule out parts of the parameter spaces that you don't believe that the data are or the posterior parameters should be in. It converges always to maximum likelihood estimates. So in the limit that we actually have lots of data, we get to the same values we'd expect for maximum likelihood. And a good conjugate prior has readily interpretable hyperparameters that we can use to kind of describe the nature of our prior assumptions in the context of the experiment that we are doing.